All right. Hey, everyone. Welcome to lecture number 5. We're moving quickly. Almost done with our first module, which is exciting. So your first kind of due dates are coming up. So hopefully you're getting deeper into the material, and hopefully you probably all started to face some real challenges, which is important. You know, the way you learn this stuff is by having to fight through some challenges and some code here and there. So that should be hitting you pretty soon here. Your first programming challenge is due in a little bit less than a week. So I'll do some more, talk about the schedule a little bit more in a second, but I'm going to go ahead and hand it off to Rohan and Arvind for a few announcements.
Okay, Professor. I'll share my screen for AutoLab.
Mhm.
Is the screen share coming through, Professor?
Loading, for me it's still loading. Let's see, I think it's coming though, just give it 1 second. It's still loading for me.
Yeah, even
for you as well, Arvind? Okay, now I have it. Yep, got it.
Okay.
Perfect.
So hello guys. Our AutoLab server where you guys would be submitting your assignments is up now. This is our first assignment, the original problem. Just a minute. So if you haven't created your account yet, so the accounts are created for you. If you haven't logged in yet, please go to the link autolab.welchlabs.org. Over there, you can click on the forget password button, and you would be able to create your own password and be able to log in into this. Over here, we have few things. There's this checkbox which you have to tick while submitting your assignments. This it says that the work you would be submitting is your own and haven't copied it from anywhere. On the submit button, you'll be able to submit your assignments. We have a small thing of our scorecards where you would be able to keep a track on who has scored how much and what's the highest score by now. So the highest score till now is 10, and then there's 9 of a student. So yes, this is about AutoLab. Please feel free.
Great, and then just one quick little thing. This is great, Ron. Thank you. Just one thing I wanted to jump in really quick. So you can see the scores there, and we're also, I think the table, Rohan, I think it's ranked by accuracy.
Yes.
I believe is that okay? Cool. Yeah. So the winner of the prize, I think we're offering a $10 Amazon gift card. Is whoever has the highest accuracy. So right now it's TA number 1. Is that Arvind or Rohan who's winning right now? You guys obviously aren't eligible, but but yeah, okay, great. So the winner right now is Kratos, it looks like. So great. So there you go. Sorry, go ahead.
So yes, that's about AutoLab. Feel free to ask any doubts if you have. There's one more thing that I would like to share is about project proposals. So there are few project proposals coming in, but we would encourage you to submit your resumes with it, so that we could group you with someone else if you have to be. So please submit your resumes with the project proposals. Okay, that's it, Professor, from my side. Arvind, do you have anything?
I would suggest the students to put both the files in a separate folder and zip it and put it on Canvas. That would be easier for us.
Yes.
instead of putting two separate files. And regarding the assignments, only NumPy is allowed to be used, and then no other library could be used for the assignment. I just wanted to make sure.
Also, I would like to address the error on Piazza. So the error is about your time. The time you guys have exceeded your time limit, which is 180 seconds, and that's the reason you have came across that error. So please try making the code a bit faster and resubmitting it.
Because we tried submitting our submission files after we saw the error screen on Piazza. So as you could see, we are able to submit it, and AutoGrader has successfully graded our assignments. And apart from that, there is one more student from this class who has submitted it successfully. So I would ask the people who could not, who has zeros here, please try to reduce the time and resubmit it.
That's it, Professor, from our side. I'll stop the screen share.
Great. Well, yeah, thank you so much, Rohan and Arvin. As you guys can tell, the class would not work without Arvin and Rohan's hard work. So awesome. Thanks, guys. So yeah, Abhijit asked how many images are in the test set. That's a great question. I don't remember exactly. I want to say like 30 or something, maybe a little bit less. Do you guys remember?
It should be more than that, Professor, I guess.
More than 30? Okay. I think less than 100 though.
Yeah.
Okay. Yeah, we can look that up if we have a chance. If you want to post it on Piazza, we can get you the number. But it's less than the training set, I'm sure. I don't recall how big. I guess the training set's actually quite large now that I think about it. So I would expect less than 100 though. It's a good question. One other thing to be aware of is that the AutoLab server is just one little AWS virtual machine. Setting up an auto grading server like this is a little bit complicated. And Arvin and Rohan have put in a lot of work over the summer to get that server set up. And there's also another student, a PhD student named Archit Pranami. And he's been very, very helpful getting this set up. But I say all this because this is a server that we maintain. It's not some like service we can get to the university. There's no, as far as we can tell, like off-the-shelf, easy-to-use auto grading services that we can use. So we have chosen to set up our own server because we think it's valuable to you to get that immediate feedback on your code. So just be a little patient and know that our server is going to be a little slow sometimes. It will run slower than your machine, almost always. So we're giving you 180 seconds, but I would try to make your code about 3 times faster. Again, you don't know exactly how many test images there are. We'll try to get that number to you, but I would assume less than 100. But just keep that in mind that it will run a little bit slower than your computer. Great. Okay. Well, anything else before we get started? We'll hop into our lecture for today. We have a lot to cover. We got a cool topic for today. And I'll just do a quick little look at the schedule with everyone. But I'll go ahead and pull that up while you guys are thinking. Let me know if anything else comes up. Maybe my screen share here.
Professor, I'll
Yes.
answer Abhijit's question.
Yeah.
There are 33 images.
Oh, my guess was good. There you go. There's 33 images, right? So I think a good target for you if you want to use your attempts carefully is try to only submit code that will take, let's say, less than 60 seconds on your computer for 33 images. You could compute how much time that is per image. I think it's probably safe to assume that the auto grading server runs about 3 times slower. It may run slower sometimes. I encourage you to submit your code earlier because if you submit it like the night before, there may be a lot of submissions and it will run slower. So the sooner you can submit, the better. And it makes our lives a little less stressful. All right, cool. Okay, so here is our schedule. Let me zoom in a little bit here. So we have made it to the 22nd, and today we're going to be talking about the Hough transform. We just barely started the Hough transform last time. And we're going to get into it in a lot more detail. The Hough transform is the last tool that may help you on the programming challenge. I don't believe that you have to use the Hough transform. Actually, just for fun, I think this is okay to discuss. Well, actually, no, I don't want to ask, actually. I'll ask you guys later. I was going to ask Rohan and Arvin if they were using the Hough transform, but actually, I don't want to know right now because I don't want that to bias anyone's thinking about what they should use. I think it's fair to say, though, that the Hough transform could be very helpful, but you may not have to use it to do well. But what we're doing with the Hough transform today is we're giving you a new technique, right? So we give you edge detection. We're going to give you another technique that you could use to solve the problem. But just keep in mind that nothing we're ever going to give you is going to fully solve the problem. It's going to take some creativity. But the Hough transform is another tool that you may find helpful in solving the programming challenge. Okay, next class we have a guest lecture with Tony Fast. Tony Fast is awesome. He's a good friend of mine. He's had a bunch of different roles. He used to be a professor at Georgia Tech. He is a master at Python and Jupyter. I'm really looking forward to his talk. We will maybe share a little more about him, or at least give a good intro next time to Tony Fast. But I'm really looking forward to his guest lecture next Thursday. Okay, I think that's all the big stuff. Just know your programming challenge is due Monday the 28th at midnight, and your project stage 1 is due the 25th, which is coming up quickly, right? It's Friday. Yep, okay, cool. Yep, so this Friday you have your first thing due in this course, which is project stage 1, your proposals, and you have the programming challenge due Monday night. All right, hopefully that doesn't ruin your weekend. Okay, cool. All right, so let's hop into it here. Let's go to Hough transform part 1. Oh, you know what I should do is I should just go ahead and preemptively turn off my video. We know this creates audio issues, so there we go. Video's off, my screen share's coming through. Let's get started. Okay. So this is Hough Transform Part 1, and the overall idea here, is hopefully by now in the course you have a good understanding of the mathematics and the code that we use to go from an image like this to an image like this, to an edge image, right? But the next thing that you're probably wondering is, okay, wouldn't it be nice to like actually detect real lines, right? So not just points that kind of are edgy, but to detect things like lines, right? That would be great. So we're not the first people to kind of want to do this. The first person who's well known for doing this is a guy named Paul Hough, who we'll talk about. At the time, he was working on this really interesting physics problem. And this physics problem has to do with a big piece of scientific equipment called the bubble chamber. So this is a giant chamber that people do particle physics in. This guy named Donald Glaser won the Nobel Prize for inventing this thing. And the bubble chamber, it involves sending particles through a liquid. And what you do is you make these images with the bubble chamber, and the images show you the path that the particle took. And by looking at the path the particle took, you can infer things about the mass or the charge or different things that you would want to know about a particle to do physics research, to understand how particles and kind of how our universe works, which is pretty cool. So wrapped up in this physics problem is kind of a computer vision problem. So let's get into that. So there's a nice video on this if you want to watch. Here's where it gets hard. So you have all these images from the bubble chamber. And I love this little video clip that I found. So this is a woman here, and her job must have been looking at these images from the bubble chamber. So she would look at a bunch of slides basically that showed images from the bubble chamber. And to actually do some of these physics experiments, they were looking for low probability events. So like certain particles might have a certain charge 1 out of 10,000 times or something. You might have to do an experiment a bunch of times to actually get statistical significance. So here's a great quote from Paul Hough. So he says, about 100,000 exposures are required in a typical experiment to obtain a sample of a few tens or even hundreds of strange particle events from which the behavior of known particles and the existence of new ones can be deduced. So really, they were working on discovering new particles, which is pretty cool. It's a pretty cool part of physics. But to do this, they had to look at hundreds of thousands of images, which, as you can imagine, gets pretty tiring, right? This is something that you may not even have enough human power to do, to analyze a bunch of images like this. So that was the problem they were trying to solve. And what Paul Hough thought about is he said, okay, can I use a computer to do this, right? Can I use a computer instead of a human to find these lines and maybe look for certain kinds of lines in these bubble chamber images? Can I find lines in images? And if you think about it, finding lines in images, that's certainly something that I think all of you are thinking about right now as part of your programming challenge, right? How can I find the lines that represent the edges of the brick, for example, because that could be helpful in solving the challenge. Excuse me. Okay, so let's get into Hough's problem real quick. So really, to put this in math terms for a second, let's assume we're giving a set of points. So here I've drawn a little figure, and I have 7 points. I have x1, y1, x2, y2, x3, y3. And the question that he was going after was, okay, how do I find the best lines through these points? And this should feel kind of familiar, right? It's very similar to what I asked you to do, or what you may be thinking about on the programming challenge. If you're trying to detect a brick, for example, you've got a bunch of points that represent the edges of the brick, and you may want to try to fit a line to those points, right? That's kind of the idea. So that's the problem that Paul Hough was going after. And let's spend some time trying to figure out how hard this problem might be, or maybe what kind of algorithm we could use to find the best set of lines for a given set of points. Okay, so let me zoom in a little bit here. This is really small. Let's try this maybe. Yeah, it's a little better. Maybe one more. Okay. All right. So just thinking through this, and whenever you're learning something new, I really encourage you to, when you have the time, sometimes you're going to be a little bit rushed, but hopefully your school is structured in a way that you have enough time to really think about stuff, because that's really how you're going to learn. I like to think through, how would I solve a problem before I look at what, people in the literature have done. And I don't know, if I was Paul Hough, I might have done something like trying all the lines, right? So I might have just said, okay, here's a bunch of points, right? Can't I just look at all the different possible lines that would exist between two pair of points and then see if those fit the other points reasonably well, like by measuring how far off the other points are from a line, for example? Couldn't I do something like that? Couldn't I just try all the lines? So that is, I think, a reasonable approach, and hopefully that idea makes sense to you. I think if I was Paul Hough and the year was 1960 or whatever, and I was trying to solve this problem, I might try that first, right? And maybe he did. We don't know exactly, but maybe he did. So let's spend just a little bit of time thinking about that approach of trying all the lines. And we're now arriving on our first poll for the day. And what I want you to think about is given n points, right? So let's say we have a number of points called n, right? Here it's 7, but it could be anything. Approximately, not exactly, but just approximately, how many lines would we need to test, basically, if we were going to test all possible lines? So like here's one line we'd have to test, here's a line, here's another one. There'd be another one from here to here, of course. There'd be one from here to here, right? So in general, what I'd like you to spend 30 to 6, let's say 1 minute thinking about is thinking about how many pairs you'd have to test. Is it n cubed over 3, n squared over 2, 2 to the nth, or 2 to the n minus 2? So let's go ahead and open up the poll when you guys are ready, Arvind and Rohan. Let's please take 60 seconds, and then we'll look at the answer. All right, great. So we have the most votes for B. Let me go ahead and switch my screen share real quick to my drawing application. Cool. All right, there we go. Hopefully you can all see that. So yeah, so the most votes were for B, and let me zoom in just a little bit here. Okay, cool. So there's a bunch of ways to think about this, and I have a little explanation in the notebook that you can read later if you'd like to, but here's one way I like to think about it. So we want to figure out how many lines we have to test. So what I did is I started thinking about, I kind of drew this matrix, and I said, okay, let's give our points names. Like let's call this point A, let's call this point B, let's call this point C, right? And we know that, for example, between A and A, there's no line that could happen, so this couldn't be a line. But between like A and B, for example, there could be a line there we'd have to test, right? So between A and B, there could be a line. Between A and C, there could be a line. Between A and D, there could be a line, right? So that's 3 lines we have to check so far, right? Now what about here, right? For A and B this way, do I have to check this? I check the line between A and B? Do I have to check the line between B and A? What do you think? Throw it in the chat window. No, yeah, so Dinesh, good job. We don't have to check this because we've already done it. So a line between B and A is the same thing as a line between A and B. So I'm not going to check this. B and B I don't have to check really, right? So B and C I haven't done that yet. And then C and D I haven't done that yet. So hopefully you can start to see a little bit of a pattern forming here where we have to check, this is an X2. We have to check kind of this upper triangle. Hopefully this makes sense, and you can imagine making this really big. There's kind of this upper triangle of pairs we have to check. And what I like to really think about, here we go, cool. So it's kind of like this stuff, right? So this is like n over here, right? We have n of these, and this goes on forever possibly, right, n. And this is also n over here, right? So if this box was completely filled with check marks, right? If we had to check every single possible pair, how many pairs would that be exactly? Throw it in the chat window if you know. So if Yeah, in square. Oh, you can't really write squared, can you? I like that. In asterisk asterisk 2, right? Yeah, so in to the power of 2, right? Good. So that would be in squared. But because we're only checking like half of them, because it's just like half this thing, it's approximately n squared over 2. It's actually like this minus n over 2 or something, but just approximately it's about n squared over 2. The big point is that it doesn't grow this fast. It's not like 2 to the n or anything like that. But yeah, you have to check n squared over 2 points. Hopefully that makes sense. Let's keep moving. If it doesn't, go back and look at those notes, post on Piazza if that's confusing. But let's go ahead and hop back to the lecture. Here we go. Okay, cool. That was a fairly seamless transition. So the answer is B. And the reason I bring this up is because I want to think about how feasible this is. And if you want to look later, here's my kind of written explanation of why the answer is B. So here's the thing. So since we have to compare n squared over 2 points, like I mentioned, this can start to get really, really expensive and really, really slow, even on modern computers. So like, for example, here's a little bit of math. This can be really, really slow because like in the above images, these are 256 by 256. They have on average, let's say 500 edge pixels, which makes for around 100,000 lines to test. And 256 by 256 images are actually pretty small. In practice, you know, like the video stream you're watching now is probably HD or full HD. So you're talking about a resolution of 1920 by 1080. You end up with just a huge number of pixels to test. So this quickly becomes computationally intractable, where we just don't have enough time to try them all, basically, even with a fast computer. The other thing I want to get at a little bit with kind of our trying, just the idea of trying all the lines, is that the points that we're going to get in our image are not going to be exactly collinear. So like if we tried to like, you know, we fit this line and we say, okay, you know, is this point on that line? It's not going to be exactly on the line. So sure, you're going to need to think of some way to deal with that noise, basically. So there's a few problems with just trying to kind of brute force fit lines like you would maybe in a high school math problem. So those are two problems with that kind of naive approach. And I just pointed those out because I wanted us to talk about the Hough transform. That's really why we're here, but I wanted to point out why it's pretty interesting. So Paul Hough figured out a way to solve both those problems at once. So he has a way of finding lines that is more efficient, way more efficient, and it's less susceptible to noise, which is pretty cool. So it's kind of like a win-win. And this is what we talked about last Thursday a little bit. Now I'm going to get into it in more detail. So his idea might seem kind of random. Apparently, he thought of it walking home from work one day, which I think that's interesting. I think most of any ideas I've had that are any good mostly come when I'm doing something other than working, which is kind of funny. So this idea came to him apparently. I don't know how he thought of this. It seems like a really random idea, but we talked about this last time. Let's talk about it again. So this is the idea. So we're going to map our points to a new space called Hough space. And just so you know, we're going to be doing what's called the Hough line space, but there's also a Hough space for circles. There's a Hough space for ellipses. It just takes a little more time to do the math, but this is going to be Hough line space, but there's other Hough spaces as well, which may be helpful in your programming challenge. Okay, so his whole idea was let's take each point and instead of showing this as a point in our space, let's transform each point into a line. And his idea is that the y value of the point is going to become the slope of our new line, and the x value is going to become the y-intercept. And in Hough space, I'm going to use the letters u and v to represent kind of what we normally call x and y, because we're using x and y to represent our Cartesian or kind of our normal beginning image space. Okay, so this point becomes this line, right? So the 3, which is the y-intercept here, or the y value, becomes the slope. So this line has a slope of 3. So we go over 1 up 3, over 1 up 3. And it has a y-intercept of 0. So this point becomes this line. So the slope is 2 because the y value of this point is 2. And the y-intercept is 2 as well because the x value of this point is 2. And so on and so forth. And I'll go ahead and ask the class again. This was a big theme that we touched on last time, but just to make sure we all get it here. What is maybe surprising or special or interesting or unique about these 3 lines? What's maybe a little surprising? Yeah, so Pooja, Manesh, got a good job. Yeah, so these all intersect at one point. And that might seem counterintuitive, right? I don't know how Paul Hough thought of this. I never would have thought of this, ever. I don't think, never would have happened. So yeah, so it seems like collinear points in Cartesian space intersect at a single point in Hough space. And maybe we can use that to find lines. That's the whole idea here. That is the whole idea of the Hough transform. So here's a fun animation that we looked at last time, where I actually do the Hough transform of a real image. And it's pretty cool. You can see that the points I draw, the ones that are collinear, do end up intersecting at single points, which is pretty neat. I think that's pretty cool, right? That this actually works. Now, just seeing it work on the screen in an animation is one thing, but it's another thing to actually understand the math that makes it work. And if you're going to program the Hough transform, you actually have to know the math. Really, that maybe you could work your way around it, but I think it'd be difficult. I think you do have to touch the math here, and I think by doing the math, you're going to have a deeper understanding of how it works. So over the weekend, I left you with a little challenge, which was to prove this kind of hypothesis we have, that collinear points in Hough space, that collinear points in image space create lines that converge at a single point in Hough space. Now, if you had some time to work on that, great. If you didn't, that's okay too. But what we're going to get into now, I'm not going to answer this question right away. I might answer this a little bit later. I'm not going to be asking you to prove this on your quiz or anything like that, but we are going to use some of the math that you need to prove this to actually code it up and stuff. So let's move on. I won't prove it right now. We might bump into the proof later. We'll see if we have time. What I want to get at is something a little bit more practical, because let's say that you went to code this up, and maybe it's not clear how we would program this yet, and that's okay. Doing a little bit of math first, I think, is going to help us clear that up. What I'd like us to think about is, where will our intersection happen? So this will be our second question of the day, and this one's a little harder, but that's okay. And if you don't get all the way there in the 60 seconds, that's totally fine. Really, I just want you to take some time to think about it. Before we open the poll, let me just talk about the problem in a little bit more detail. So here's the problem. So given a set of collinear points, so these points along the line y equals mx plus b in image space, where will the lines intersect in Hough space? So this point, we're going to call this point u1, v1, right? And what I'm trying to get you to do with this math is draw a direct connection between the slope and the y-intercept of this line in image space and the point u1, v1 where these lines intersect in Hough space. That's what I'm trying to get you to do. Notice that all the answers are in terms of m and b, right, which are parameters of this line. So let's go ahead and open it up, take 60 seconds, and then we'll talk about the answer. Okay, great. So let's see. The most popular answer was C. Great. Second most popular was A. Cool. All right. Great. So let's get into talking about how we should, or one way to think about this. Let's get into looking at an answer here. So let me share my drawing screen again real quick. Okay, there it is. Great. Okay, cool. All right. So let's start thinking through this a little bit here. And what I'd like us to think about, or kind of the way I'd like us to think about it, is let me go ahead and start with a little bit of an equation. Let me scroll this here. Cool. All right. So let me put an equation here. So for this point, right, this point here, u1, v1, right, this is on all three of those lines, right? So this point has to satisfy each of these lines. So I can write an equation like this. I can write, excuse me, I can write V1, or actually I'm just going to call it, actually no, I'll say V1, excuse me. So V1 is equal to yi, so any I value, any y value, times u1, which is our other point, plus xi. Okay, so let's have a second to look at that. Really, I've just taken one of these equations and I've just written it in terms of any y or any x. And the reason this is true is because, so U1 and V1 are on all three of these lines. So we're kind of starting by assuming that they do intersect. I'm not doing the proof right now. I'm just showing how to get to the answer here, how to determine the intersection point in terms of the slope and y-intercept of that line. So that's the first thing, is I just kind of restated that. And now I'd like us to do just a little bit of rearrangement here. What I want to do is I want to take this equation that we just figured out, right? And I want to rearrange it to make it look like that equation. And the reason I want to do that is because then it'll kind of fall out what these parameters should be. So this is the equation for Hough space, but it's connected to this space because all these x's and y's, right? This line is along those points, right? So these x's and y's have to work for this line. So what I'm going to do then is I'm going to just rearrange this. So we're just going to do a little bit of algebra. Basically, I'm going to solve for y. So I'm going to subtract this over here. And at the same time, I'm going to subtract this over here. Maybe there's a nicer way to do that. Oh, actually, you know what I'm going to do? Here we go. I'm just going to subtract this to that side is what I'm going to do. So I'm going to switch. I'm going to do y times u1 equals, it's going to be v1 minus x. So all I've done is just subtract that x over, and I just lost the yi xi for a minute. And now I just want to totally solve for y. So I'm going to get y is equal to, I'm going to get v1 over u1, like that, minus x over u1. Okay, I think that's coming through okay. All right, cool. All right, and we're almost there. Now I'm just going to make this look a little bit friendlier, right? So I'm going to do y is equal to, I'm going to put this one first. I'm trying to kind of put this in y equals mx plus b form, minus 1 over u1 times x, okay, plus v1 over u1. Okay, so all I've done is I've taken an equation that kind of has to be true in Hough space if those points intersect. I'm kind of assuming they intersect. And if they do, I've just rearranged that equation to match the way it's represented here. Because now I think the answer is just going to kind of fall out, I hope. Because now that I've rearranged it, so I know that since these points go through that line, that this equation has to be true. So this m here, right here, this must be the same m as this term. So this actually gives us the slope. So the idea here then is that since this is the constant that ends up in front of x, then m, our slope, must be minus 1 over u. I apologize for the bad handwriting. My handwriting is slightly better on the whiteboard, but not that much better actually. Cool. And then so the b value, hopefully this makes sense. B is just going to be this term. So b is v1 over u1. So if we look at our answers then, oh, and actually in the answers I solved for v1, there's actually one more step, apologies. So let me go ahead and get this written down. So b is equal to v1 over u1. I think that's a little bit off screen. Let me zoom out a little bit. Cool. Oh, it's just this a little bit cropped. Okay, cool. All right, great. And if you go one more step, you'll get u, for example, and I really should have a 1 there. U is equal to minus 1 over m. Minus 1 over m is our u point. Okay, u1 is equal to minus 1 over m. So it looks like C is probably the answer. Let me confirm. Yeah, so minus 1 over m. And then if we solve this equation for, we have to do a little substitution, but I think we'll end up with C. Okay, cool. All right, so hopefully that makes sense. If it doesn't, feel free to ask on Piazza. This is a little harder than what I'd ask you on a quiz, but not too much harder. So there we go. And what I kind of want to get at here, just for a second while we're thinking about it, remember the whole point here is that we can program up the Hough transform, right? We can go write some code that does it, right? And we're about to actually run into a problem with the Hough transform in a second. We're going to run into an issue that Paul Hough wasn't able to solve, really, not elegantly at least. And it has to do with some of the algebra we're doing right here. You know, whenever you're dividing by a variable, you have to always think about, hey, you know, what if m is 0? What's going to happen? So just tuck that away in the back of your head for a second. But this is how you find the intersection point in terms of m and b, basically, which is going to be really important because, as maybe you're starting to guess, we're going to actually solve the computation problem in Hough space, and then we're going to use that to figure out m and b to fit the line in image space is kind of the idea. It's kind of a common idea in math. There's a transform in mathematics called the Fourier transform, where we actually solve math problems in different domains and then bring them back to the original domain. And it's actually easier to solve them in a different domain, which is pretty cool. Okay. So that's great. Hopefully that all makes sense. I have an explanation in here as well as well as the proof, if you want to look at the proof for this. But that's just a little bit of math that's going to help us program up the Hough transform. Okay. Cool. So there's our animation again. Great. And I think that the last thing I want to emphasize here is that with this proof in hand, and I haven't walked you through the entire proof, but the math we just did gets us actually most of the way there. And like I said, if you're interested, feel free to look at that proof if you'd like, but I'm not going to ask you to prove it on a quiz or anything. But it turns out that it's mathematically true that the problem of finding collinear points in image space is actually mathematically equivalent to finding intersecting lines in Hough space. And it turns out that finding intersecting lines is actually much computationally cheaper, which we'll see soon. Okay. So that's great. Let's get into some problems. So like Paul Hough figured all this out. Great job, Paul Hough. Way to go. But he kind of missed a couple things. There's a couple of problems he had. And I think we'll go ahead, let's go ahead and look at one of the problems he had. And there's just a couple things he missed. And really it would take another, I think, 5 or 10 years for researchers really to arrive at the modern Hough transform. Let me just show you one of the problems. So one of the problems he had is he didn't quite know how to find the intersecting lines efficiently. Okay, bit of audio issue. So my video's off, right? Video's off. Okay. How is it sounding now? How does my audio sound? Anybody?
Yeah, it's good. It's good, Professor.
Thank you, Arvind. Okay, great. When I first asked that, no one typed anything, which I thought meant that I was totally disconnected. Okay. So let's get into the problems. And I just want to go ahead and point out one of the bigger problems with the Hough transform. So here we go. Let's look at this animation. So take a second and watch this little animation with me here. So you can see I'm first drawing a vertical line. No problem. Look at that nice intersection, right? Now I'm drawing a slanted line, no problem. Okay, now here I'm going to draw a horizontal line. And throw it in the chat window. What issues do you see with the horizontal line? What's the problem in Hough space? What's the problem with the red line? Yeah, and actually there is an intersection. Like they will intersect actually, but they intersect at infinity. So yeah, that's right. Good job, Ravina. Yeah, excellent. The intersection is way off at like infinity. Exactly. And I touched on this just briefly a few minutes ago. Does anyone know why? Why is the Hough transform ending up with an intersection at infinity? Yeah, the slope is very close to 0, and we had that 1 over m term in our math, right? We had a 1 over m, so it blows up, so u equals infinity, so we can't find the intersection. And the entire Hough transform strategy, we haven't programmed it yet, right? But the whole strategy depends on finding intersecting lines. And if you have to make your Hough space grid so big that it goes to infinity, you're back to having a computational problem. Now, Hough did propose a solution. He was aware of this, but his solution is kind of half-baked. He proposed that you just solve the problem twice. So you solve it once, like it is now, and then you rotate it 90 degrees and you solve it again, and you throw away all the ones you can't find, basically. So he proposed just solving the problem twice, but rotating it 90 degrees in between, which would work. You know, it's a solution, right? But it's not terribly elegant, and there was a few other problems with his implementation that we're going to get to now in part 2. So that's a quick look at the Hough transform. And you can read his patent on this if you want. It's really interesting. He really only had half the idea. What we're about to hit in part 2 really makes the Hough transform work. So let's get into Hough part 2. So And this is the last lecture we'll have on Hough, so we'll get as far as we can. Let's see, how much time? We're not doing bad on time. We have about 35 minutes. These lectures go fast. Okay. So we'll make our 35 minutes count. You may have to catch up a little bit. And I'll just say that in general, in terms of your programming challenge, I would like you to understand as much of this stuff as makes sense for you. I am requiring you to do these programming challenges, but if you end up not understanding how every little detail of the Hough transform works, that's okay. You know, I'm not going to quiz you on every single detail. The quizzes are going to be mostly similar to the questions I ask you in class. And I say that too because don't let your understanding of the Hough transform slow you down in terms of your programming challenge. At the end of this notebook, right, I'm going to give you the Hough transform implemented in a nice Python method, right? So let's see, where is it? So if you scroll way down here, it's probably in a .py file as well, but if you scroll way to the bottom, yeah, there it is. So here's the Hough transform wrapped up in a nice class. And you're welcome to use this. You can use my code on programming challenges. Now, to use my code, you're probably going to have to learn some of the notebook. And I would like you to learn all of it, really, but I know that we all have limited time, right? So what I'd like to do in the next 35 minutes is give you the best understanding I can of the Hough transform. And whatever else you're able to look at and learn on your own is perfect. And just make sure you're able to answer the questions that I ask you, the multiple choice questions that I ask you, because that'll be similar to what you see on the quiz. And then beyond that, I would encourage you just to have enough understanding that you can do the programming challenge well. And then if you have time and you're curious, then you can dig deeper. It's really an interesting subject, and you can really learn a lot from it. But I'm not going to require you to be an expert on the Hough transform. Okay, so I'm going to tell you another story. So let's story time. Let's talk about one cool story here. So that was the original Hough transform, and it kind of worked, kind of didn't. It would really take some researchers at Stanford, at the robotics group at Stanford, to really improve the Hough transform. So this is a little robot called Shaky. I think it was the world's first autonomous robot, I believe, or maybe first mobile robot. But it would navigate little rooms. What's really cool about Shaky is that despite how big it is, look how big it is, right? The compute is actually not on Shaky. So that little antenna, it's a wireless connection to a giant mainframe computer in another room that does all the computation. And the video you're watching has been dramatically sped up. And in reality, Shaky would like take a picture, send the picture for analysis to the mainframe computer, and then wait like 10 minutes, and then it would get instructions about how to move. So it moved insanely slowly, right? But this is like the grandfather of autonomous cars today, right? It's this little robot at Stanford, and I just love this old video. I think it's pretty cool. So here you have Shaky trying to navigate its environment. Okay. Cool, so that's Shaky, and here's another cool little clip where they're showing how Shaky navigated its environment. So Shaky's taking an image there, and look what happens. Shaky is finding edges. So you saw that. That's probably a Sobel edge finder, probably is what we're looking at. So Shaky looks down, takes an image, does the edge detection, and then, as you may have guessed, Shaky is going to do a Hough transform, which we'll get to in a second. But not the same Hough transform we just learned. It's going to use kind of the grown-up version of the Hough transform that the researchers at Stanford invented while programming Shaky. Okay, so let's talk about those researchers. So this is the group that worked on Shaky, or at least part of the group. And these two researchers, Richard Duda here and Peter Hart over here, they really made the modern Hough transform that we're going to use in class. They also wrote a fantastic book on computer vision. I used a quote from it in the opening of this course. It's, what is the quote? It's, we are all experts at perception, but none of us know much about it, something like that. So they wrote a really excellent book on computer vision back in the 70s. But they really came up with the modern Hough transform. So basically, you know, way back in the 60s, they were building this robot, and they had similar problems to what you have today. So they had a problem where they were trying to find lines, right? Just like you guys are, okay? And they didn't have such a helpful professor like you guys do, because no one really knew this stuff yet. So they went and read the only computer vision book that was actually in print at the time, and it's this book. I have a copy if you're interested. It's pretty cool. You can buy it on Amazon for really cheap because it's old, but it's really cool. This is the first computer vision book written by this guy named Azriel Rosenfeld. And in this book, there is a quick description of the Hough transform. Here's the page that describes the Hough transform. And it's Hough's original implementation, so it's not really complete. It still has some problems. So, Hart and Duda, these researchers at Stanford, find this book, they find this method, and they think, okay, this might help us, but it's not quite everything we need, right? We're missing one little piece. So it just so happened that at the same time, Peter Hart, he was examining another approach that he thought might be helpful. It's this mathematical approach called integral geometry. And it's a little bit of an abstract part of math. But in this approach, or part of integral geometry for certain problems, they use a different representation of a line. So I think most of us, learn the representation of a line, y equals mx plus b or something like that, and the slope-intercept form of a line. But there's a whole other representation that's actually way more helpful here. And it's this angle radius representation. So let's look at this for a second. So there's another way to represent lines. This way of representing lines still uses two parameters. But instead of the slope and the y-intercept, we're going to look at the angle that a line that goes from the origin and intersects our line at a perpendicular angle makes to the x-axis. That was a long sentence. Let me explain it a different way. We're going to look at two things, basically. So one is the distance between the origin and the line, and the other is the angle that that distance vector makes between the x-axis and the shortest distance between the origin and the line. So a little clunky to explain in words, but hopefully this image helps. So this is another way to represent lines. And by doing this, and yeah, it is similar to polar coordinates, Christina. Yeah, that's a great question. It's not exactly the same because we have this like perpendicular line, but there's a lot in common. Yeah, great question. Cool. All right, so that is the representation we're going to use. And let's just do a little bit more math just to kind of get you thinking here and to help you understand why we're programming this the way we are. So here is our third poll of the day. And let me walk you through the question, then we'll open up the poll. So here is our old friend y equals mx plus b. And I want us to be able to translate back and forth between y equals mx plus b form and this new format of the line. So let's just start by trying to figure out the y-intercept, b, right? So what I want you to do is take 60 seconds and try to find the equation for b, the y-intercept of the line, right, which is this point here. It's also the distance between here and the origin. It's this distance right here. I want you to try to find an equation for b in terms of rho and theta, in terms of these two variables that we're going to use for our new line representation. And this transformation between y equals mx plus b and this rho theta form is going to be very important when we go to program the Hough transform. Okay, so please take 30 seconds, or 60 seconds, excuse me, and we will look at the answer. Okay, great, thanks. All right, and just so I'm thanking the right person, who's running the polls today? Is it Arvind or Rohan?
It's Rohan, Professor.
Rohan, thank you, Rohan. I appreciate it. All right, cool. So we have about a tie between A and B. Perfect. All right, let's get into it. Okay, so let me change my screen share. Okay, let's go here. Great. All right, cool. So here is my picture that I can draw on. So I have added, let me zoom in just a smidge. Cool. So I have added a little line here to show that, this length is B. This is the y-intercept. That point, from the distance between that point and the origin is B. Quick question to the class. What is the value of this angle? This probably feels like the SAT or something. What is the value of this angle? Throw it in the chat window. It might be 45, but it could change. It could be anything. Okay, so I see a 90 minus theta and I see a theta. Okay, one of you is right. So let's do this to get there. So let's do, so what is the value of this angle right here? So throw that in the chat window, please. What about this angle right here? Yeah, this is 90 minus theta because together those two make a right angle. So this is 90 minus theta. Cool. All right, and then if this is 90 minus theta, and this is 90, and this is the leftover, and we know that this is a triangle, so the sides add to 180, or the angles add to 180, it turns out that this one has to be theta. So the answer that I was looking for is this is also theta right here. Hopefully that makes sense. All right. Okay, so we're almost there. So what I want to get at now is I'm trying to find B, or an equation for B, and I have rho, right? So if I'm looking at this angle for a second, right, I have the opposite side and I have the hypotenuse. So if I'm using, and everyone learns this differently in high school, I'll just talk about how I learned it. So I learned SOHCAHTOA. So I learned that if I have the opposite side and the hypotenuse, then I should use the sine. So I'm going to write down sine of theta, is equal to the opposite side, which is rho, divided by the hypotenuse, which is b. And if I solve this for b, if I get b alone on one side, I believe that I get b is equal to rho divided by sine theta, which I think is a, which I think was a tie for first place. Okay, hopefully that makes sense. So that's how we find the y-intercept in terms of the rho and the theta. And we're about to use that to code up the Hough transform. So great. All right, hopefully that makes sense. I think I have one more question for you real quick, and then we're going to get into some code. Let's go back to the lecture notes. Share. Cool. All right, so that's that. And now I have one last question for you. And actually, there might be one more question, but I might skip it. We'll see. Okay, so here's either my last poll for the day or second to last poll. We'll see. But hopefully the math I just did made sense to you. And there's one more piece of math that I want you to do now. So you found the y-intercept, b, in terms of rho and theta. Now I'd like you to find the slope, right? How steep is this line in terms of rho and theta? So again, please take 60 seconds. I'm going to go on mute, take some time, think about it, and then we'll discuss the answer in 60 seconds. All right, great. Okay, so we have a lot of votes for B and a lot of votes for D. Okay, great. And the only difference between those is the direction of division. And I didn't trick anybody with A, man. Okay, cool. All right, so let's look at the answer here. Let's kind of walk through it together. So we already know that this distance is rho over sine theta. And a very useful definition of slope that I use all the time that I learned in 7th grade or something a long time ago was that the slope equals we called it the rise over the run. And you may have learned something a little bit different, but I think generally, the fancier math way to say this is that it's delta y over delta x, change in y over change in x. And one way to solve this problem is to figure out, okay, what is the change in y? Like, let's go from here to here, for example. What is the change in y over this distance? And the change in y is rho over sine theta. We already figured it out in part 1. So if we can find the change in x, then we can just divide the rise over the run, and we'll get the answer. So that's the strategy I took, or I usually take. So let's figure this out real quick. So we have an angle theta here. We have the hypotenuse, so we're interested in the hypotenuse. and we have the adjacent side. So should I use sine, cosine, or tangent if if I'm interested in the hypotenuse and the adjacent side? Which one should I use? Thank you, Ravina and Akshay and everyone. Good. So we're going to use cosine. So I'm going to say cosine of theta is equal to the so ca, so adjacent over hypotenuse. There we go. So rho over, and should I give this a name? Let's give it a name. We'll just call it x in this case. So we'll call it x. So if we solve for x, we're going to get x is equal to rho over cosine theta. Okay, great. All right, and then now to use my kind of little formula here, that slope is the rise over the run. Oh, that was a terrible circle. Gosh, that really got out of hand. Okay. All right, so it's the rise over the run. So the rise it's rho. We have rho over sine theta for the vertical change. And we have rho over cosine theta. Rho's are getting worse and worse for the horizontal change. And then the way I learned this in high school is you flip the bottom over. So this is equal to rho over sine theta times, I flip this over, so I have cosine theta over, cosine theta over rho. My rho's cancel out, and I'm left with cosine over sine. Now, I believe we actually need to have a negative in here because it goes downhill. So that's one thing I kind of skipped over a little bit. Actually, I really should have put a negative from the beginning because this is actually a change of like negative because we're going, the y-intercept's not negative, but really I should put like a negative here because I believe the right answer is going to be, I believe it's D. Did I trick, can you show the poll results again, Rohan? I forgot how many voted for D, apologies. Thank you so much. Okay, good. All right, great. I was worried that was the one that, right. So this is the right answer. It's D. Let me go double check myself by looking at my own notes just to make sure. So negative cosine over sine. Yes, cool. That's the right answer. Great. All right, so hopefully that math makes sense. And we had to put a negative because we're going downhill. I would ask you a slightly easier version of that math on your quiz. And the reason I'm showing you all this, of course, is it's going to inform how we code this thing up. So that's how you go from the y equals mx plus b form to the rho theta form. So hopefully that all makes sense. Let's get into some details here. And I have another question for you, but I might skip this one for now. Let's see, did I put the answer in the answer is not quite here, but that's okay. I don't think I'd ask you exactly this question on the quiz, but have a look at this one later. I'll come back to this if we have time, but I want to kind of get into the implementation. So it's just this was another question to further promote your understanding of this representation of the line. Okay, so let's start getting into implementation a little bit. So we're going to use, as you've probably guessed, this new representation of the line. So we're going to use this new representation. And this gets actually really, really interesting. So, and this question kind of, we'll get to it a little bit, but I guess what I really want to land on is here. So let me just show you this briefly. So, you know, in the second question that I asked you, we found that the slope was negative cosine over sine, and we found that the y-intercept was rho over sine. So if I plug those two in to y equals mx plus b, I get this equation. And I can rearrange it really nicely like this. So I get, in terms of my y and x values in my like original image space, my equation for a line is rho equals y sine theta plus cosine theta. Okay, so this is a nice representation of a line. And we can use this to make a new Hough transform, basically, right? So the Hough transform is going to work just like it did before, but now instead of mapping to a slope and a y-intercept, we're going to map to an angle and to a direction, or a distance, basically, to a rho and a theta. So what's really interesting here, let me go ahead and ask the group to take a guess. So with this new representation of a line, and we're going a little fast here, but hang in there with me. Any guesses about the kind of shapes that will appear over here, right? It's not going to be lines anymore. Any guesses? Throw it in the chat window. I'm about to show you what this, yeah, it's right. So good, Thomas. Yeah, so it's going to, because we're dealing with sine and cosine now, these points are now going to be mapped to curves, to sine and to cosine curves. So let me show you. So what we do is we take this point, and the coordinates of this point are 0, 2, right? So that 0 gets plugged in here for this first, the 0 gets plugged in here for the x value. The 2 gets plugged in here for the y value, and this is that equation we just figured out from rearranging the math we just did. And we get 2 sine theta, right? And 2 sine theta, that's a sine wave. Does anyone know the amplitude of that sine wave? 2, yeah, thank you, Abhijit, good. So it has an amplitude of 2. Let's have a look at it. So here is the sine wave. And I'm just plotting it from 0 to pi. You'll kind of see why in a second. But I'm plotting basically half of a cycle of this sine wave. So let's plot another line. So this line has a y value of 2 and an x value of 2. Is that a typo? I think it's a typo. I wonder if I'm plotting it right still though. Interesting. Okay. So this should be a 2. Yeah, I'm not sure why that's a 4. Let's look at another one. And then this one, oh yeah, I put them in the wrong order. So yeah, apologies. So these should be flipped basically. But the big point that I want to get across here is that when we take these points and map them to sine and cosine waves, we end up with 3 curves. And the really delightful thing that I think is pretty cool is what is still true about these curves that was true of the lines in the original Hough transform. What's still true? They still intersect, right? So if we can find this intersection point, we can solve the problem. Now, by switching to this representation, we've done a couple things, but one of the really nice things is what problem have we eliminated? And I'll prove it to you in a minute, but what do you suspect, right? What problem have we fixed by using sine and cosine instead of, horizontal lines now intersect. The infinity problem is fixed. And the infinity problem is actually more than just like a little semantics thing, because if you have lines that are close to flat, they're going to intersect at very, very large values, it'll require you to have a huge grid. And having a huge grid over here is computationally expensive. It takes a lot of compute time and power. So by doing sine waves instead, you're like constraining the possible output values. So you're making the problem a lot more tractable, basically, is what you're doing. So this is the improved version of the Hough transform, and I think I have a video for you. Here we go. This is fun, right? So now we're going to do the new version. So here are the sine waves that each line or each set of points gets mapped to. And notice that each of them have a nice intersection, right? So all the green points get mapped to, all the blue points get mapped to all these blue lines. They intersect right there. All the green points, and every point on this line really is a point. All the green points get mapped to all these different sine waves that intersect here, and all the red points get mapped to all those different sine waves that all intersect at one point. So by switching to representing our lines using this sine cosine formula, we have a tractable problem now that we can actually solve. Okay, all right, we've got about 10 or 15 minutes, so I'm going to keep moving just to get you into the implementation a little bit. And there's one last thing to do, basically. So we talked about avoiding intersection points at infinity, but there's kind of one problem left, which is how do we actually find those intersection points? We haven't talked about that yet. So let's get into it. So the author of this book, Asriel Rosen, so remember that Hart and Duda, these are these researchers at Stanford, are trying to solve this problem to make their robot drive. And they read this book, right? But Asriel Rosenfeld, the author of the book, I don't believe he had any solution to this problem yet. Right. Actually, no, I take that back. I'm sorry, I read this wrong. I haven't looked at this in a little bit. Right. So he actually presented an idea. Yeah, there you go. Cool. So he presented an idea, a way to find those collinear points. Great. So let me show you what that idea is now. Okay. Cool. Right. So let's walk through this. Yep. Cool. Okay. Great. I want to make sure I'm pointing you in the right direction. Okay. So let's look at this figure. So here are some points, right? That came from one of the images in your programming challenge. And I've colored the points. Can anyone tell me where these colors come from? What do these colors represent in this image? Throw it in the chat window if you know. Arctan, yeah, sure, we get them by using the arctan, but what do they represent? Yeah, direction, right? So they represent the direction. So like, this yellow value is maybe a value around pi, something like that. This is maybe 0, something like that. So they represent the direction that the edge goes in. And I've mapped every single point in this image, all these points, there's probably several hundred. I've mapped each of them to Hough space. And we know that using this this new representation of Hough space that uses the rho theta representation, we know that every point becomes a sine wave. And you'll notice you see two very strong intersections, right? So look at this really strong intersection right here, right? What does this intersection, what does this kind of correspond to in this original image? What does this, you know, in this original image here, right? What does this, why do we see a strong intersection here? What does this correspond to in the original image? Throw it in the chat window. Sean, it's a good guess. Corner, not quite right, good guess. So Abhijit, good guess as well, not quite right, good guess. So yeah, so I see some folks saying edge. Be more specific. It's not just any edge. Collinear points, sure. It's the top edge, right? And you can kind of see by the colors. So all these points on the top edge, right, they have the same direction, so they have the same color. When they get mapped to Hough space, they intersect at one point. Remember, the whole theory here is that collinear points will intersect at a single point in Hough space. So all these points along the top here, right, they're all collinear. So they should all intersect at one point in Hough space. And where is that point? It's right here, right? So if we can find this using an algorithm, we can find this line. Like that's really the key. What about this point here, right? What set of points does this correspond to? What does this represent in the original image, this point down here? It's the bottom edge. Yeah, great, Thomas. Great, everyone. Perfect. Good, good, good. Now, let's look for one more for fun. These yellow points. I think the yellow intersection is actually right here. It's a little harder to see, but it's here. Now, the next question I want to get at, and this is kind of the last piece of the puzzle, is how do we find these intersecting points, right? How do you actually code this up, right? And this was the idea that Asriel Rosenfeld published in the first computer vision book. It's a really cool idea. So his idea was to do this. He said, okay, let's put a grid on top of our sine wave so we can compute every sine wave. Great, no problem. Let's throw a grid on top. And every time a sine wave passes through a single grid cell, so when a sine wave goes through a cell, right, that's going to count as one vote. So we're going to count for each little grid cell, we're going to count the number of votes that that cell gets, right? And at the end, we'll see which cells have the most votes. And you can imagine that cells like this, because they have so many lines passing through them, should have a lot of votes, right? They should win the election. They should win the Hough election. So that's the idea. This is Asriel Rosenfeld's idea. When you do this, you get an image like this. And we're going to do the code in a minute. But you get something like this. So you can see, and I have a color bar here to show you, these points where we have a lot of intersections end up with very high values, like values close to 400 in this case, over like around 400 votes, because those are areas where lots and lots of cosine and sine waves intersect. And that happens to be this location in Hough space. Based on the math we learned earlier in the lecture, this can tell us exactly the slope and the y-intercept of the line in the original image. That's kind of the big idea. And we'll get in here and wrap it all up, but that's the idea. Is we're going to take this grid, put it over our sine waves. Every time a sine wave passes through a grid cell, we'll have to code that up in Python. Every time a sine wave passes through a grid cell, that represents one vote. We add all the votes together, and the cells that have the most votes should be the edges in your original image. So that's the whole idea. That really is the Hough transform. So let's get into it a little bit more. And I think we have about, yeah, we got about 5 minutes, so we'll try to make it count here. Okay. So let's see, do I want to talk about the Wikipedia definition? Maybe we'll go straight to the animation. Well, no, let's talk about this for 1 second. So let me read through this. Oh yeah, so Thomas asked a really fun question. I was debating whether or not I wanted to spend a little time on it, but it's a great question. So Thomas said, he said, is it a coincidence that the bottom and top edge are at the same x coordinate in the right image? Does it map? So Thomas, fantastic question. Let's address it. Really, really good question. So let's talk through it, class. So this will kind of further your understanding. So this point here, right, this represents, remember, this top line, right? And this point here represents what? The bottom line, right? And this dimension, this direction, right, this is the theta direction in Hough space. Remember, theta tells us basically the slope of the line, right? Does that make sense? It's basically slope, right? Exactly. So should these two lines have the same slope? Definitely, right? They definitely should. They're parallel, right? So it's not a coincidence. Great question. So yeah, So maybe there's some kind of pattern you could look for in here that would help you find bricks in your programming challenge, right? If it's a brick, it should have parallel lines, right? So you could use something like that, maybe as part of your programming challenge. So yeah, great question. Really, really good question. Okay, so let's watch a fun animation. I'll skip the quote from Wikipedia for now. Let's watch a fun animation. So here we go. So what I'm showing you here is the actual voting happening. So let's try to wrap our heads around this a little bit. So here's our image space, right, XY. Here is our Hough space, right? And I'm going to add the points from our image space one at a time to the Hough space. And remember, every single point that I add is going to represent one sine wave, so like one set of votes, basically, right? And you can see that as I add more and more points, these natural spikes arise. And those are the locations where we have lots and lots of overlapping sine waves, which should correspond to lines in the original image. So our job here, really, is to find the spikes, because if we do, these spikes will correspond to the lines in this original image. So that's the whole idea, and there it is in an animation. Okay. Oh, and just one more thing. This is often called the accumulator. So I've been using the word vote. This like accumulates all the votes, right? So this is we're going to represent this in a matrix, and we're going to, excuse me, add 1 every time a line goes through a cell. And this is often called the Hough accumulator. Okay, so we have just a few minutes left. We could easily spend probably a whole lecture discussing how to implement the Hough transform in Python. Thankfully, you guys are free to use my code. It's not that crazy, I promise. But I'll start walking through it here just a little bit in our last few minutes so you have an understanding. You can kind of see what I'm running right now as I'm just running an edge detector. Excuse me. About to run a threshold to kind of find the edges of the brick. There we go. That's cool. I'm going to choose a threshold value. Here's some really nice brick edges. We end up with 1,330 individual pixels in this edge image that we would like to map to Hough space. And here's where I'm really going to walk you through each step to writing the Hough transform algorithm. And like I said, we're not going to have time for this, unfortunately, in this module to go through it in detail. What I'd recommend to you is to spend maybe 20 or 30 minutes walking through this, through my implementation. And again, my goal for you is to not understand everything. I'm not looking for perfection, but what I'd like you to do is just get a little understanding of how the implementation works. And there's a couple multiple choice questions in here. And I'll walk through each step, basically making the accumulator. There's going to be a couple more multiple choice questions in here. In general, we'll try not to give you a question on the quiz that would be a question we didn't cover in class. But it might be worth spending a little bit of time. I know this question is a little bit harder. If this question doesn't make sense, that's okay. I don't think we'll ask you a question quite like this on the quiz. And what we do here basically, and I apologize for having to give you the summary version, but that's okay. We walk through how to write up this whole thing in Python. And I want to just see if there's any points I want to draw out basically. Yeah, so this is where it actually gets pretty serious basically. So this is a loop basically where I loop through every point in the image. Here I'm actually doing the Hough transform. So this cosine theta and sine theta thing, right? That's just like the math that we figured out. I'm iterating through all those points. I'm drawing these curves, and here actually is where I'm finding I'm basically scanning over the accumulator, and I'm finding all of the points that I want to vote for. Basically, I'm going through the accumulator, and I'm populating these values, and I get out a very similar shape to what we saw originally in my animations. Notice that it's upside down. That's partially because of how images are represented in Python. But we get to here. And then I think we have a little bit more work to do, I believe. We get to this accumulator state, and then what do we end up doing? Oh, yeah. So we get to the accumulator, and then we figure out the original lines, basically. So we do some thresholding again. I believe we threshold here. I can't quite run this right. So basically what we do is we pick a threshold, like maybe you pick 100 or something, and you say, okay, everything bigger than the threshold must be an edge or a line, and everything less than we're going to ignore. So you do some thresholding. And I believe when you use the Hough transform later, you're going to have to choose that threshold. So it may take some tuning. And then finally, we put all that together. Yeah, there we go. Okay, cool. You put all that together and you get something like this. So we've taken our brick, we found the edges, we did the Hough transform, we found the cells in the Hough transform space that got the most votes. We thresholded them, we found the top 10 or top 20 or whatever, and then we mapped them back to Hough space. So that really is the whole round trip. That's really what we're doing here. And I'll show you the whole thing in one animation here, basically. And again, I apologize we had to kind of cruise through the code. Again, you're welcome to use my code as part of your programming challenge. You don't have to understand every little piece of it, but hopefully this lecture is enough to give you the sense of the big picture. But here is a cool video of a rotating brick. And for every image in the video, we are doing the Sobel-Feldman operator, finding the edges. We are mapping to Hough parameter space. We are going to the Hough accumulator, we're finding the peaks, and we're mapping those back to the original image, and we get these nice lines. So that, in a nutshell, is the Hough transform. We are out of time, unfortunately. I could talk about Hough transform for a long time. But I would recommend spending a little time digesting this lecture, reviewing the notes to make sure you're ready for your quiz, and review this enough that you feel comfortable to use it in your programming challenge if you would like to. So that's it. That's really the Hough transform. I think we'll go ahead and wrap up there. Christina, it catches the shadow. It does catch the shadow, Christina. Yeah, good catch. I never noticed that. It's pretty interesting, right? So all kinds of stuff like that happens, right? So this is the Hough transform. It's the last tool that I'm going to give you as a way to use in your programming challenge. So really now it's all about you in the programming challenge. You've got about a week. Get to work. Post your questions on Piazza. Make sure your code is your own. All of your code must be either from me or written by you. So make sure you're not borrowing code from anyone else. We will be checking that. And yeah, good luck on your challenge. Please post questions if you have questions. Thanks for your time today. We will talk to you guys on Thursday. Have a good one.